So an important thing to get out of a college algebra class would be to recognize all of your basic functions and what the shapes of their graphs look like. And we started that process in the last section, talked about some functions, looked at their graphs, their domain and range. But of course, we said that those are the real, basic shape of those functions. And now in this section, we're going to learn transformations, which will help us graph other versions of those functions basically, but we'll find that they still have the same basic shape. And these transformations apply not only to this library of functions that we looked at in the last section, but to any function. If you know its basic shape, you can use these transformations to help you graph different versions of the shapes. And actually, if you understand these, if you put the time into learning this, it's going to save you so much time in the long run. You'll be able to picture the graph in your head more quickly than anybody could plug it into their graphing calculator or graphing program and graph it. You'll already have the picture in your mind. So I really encourage you to take the time to learn these because it will be time well spent. Okay, so we're going to look at examples to kind of set up the definition of each of these. The first set we're going to look at are the reflections. So the first one I use my example is the absolute value of x. And of course, we know what that looks like from our last section. That was our V-shaped graph. I'm just going to plug it, or go ahead and graph it. So when I use these elementary functions now that we talked about last time, I'm not going to plot ordered pairs. You should memorize those shapes. So there's y equals absolute value of x. And now we want to graph negative absolute value of x. And so when you have this function here, y equals absolute value of x, of course you have your input and your output, right? So your input is x and your output is y, or f at x. I didn't use function notation, but we could call it f at x. But it's also this expression then, absolute value of x. And so, of course, we've got 0, 0, 1, 1, negative 1, 1, etc., right? I'm not always going to do the table here, but what I want to show you is that the only thing that extra that this does to this is change the sign of all of these outputs. If you have the absolute value of x, now you're just going to change the sign. So I'm just going to write this as negative absolute value of x. And so you still get 0. Now it's negative 1, negative 1, negative 2, etc. And so the y coordinates change sign. Sorry, I think I'm off screen there. And so what happens is for the same x, your y is just the opposite sign. So all of these original y coordinates become negative and come down here. And of course 0, the opposite of 0 is still 0, so that point doesn't move. And so we still get the same shape. The same shape is key here, but we've got a reflection through the x-axis. So of course, any graph that we have, no matter what it looks like, if you're just going to change the sign of the function value, it's just going to reflect through the x-axis. So that's our first one. The next one, what I want you to notice here, we're going to compare to y equals the square root of x. I'm going to graph that quick. So 0, 0, 1, 1, 4, 2, and then it goes through 9, 3. That's our half parabola, remember? Okay, so here's y equals the square root of x. This time the negative is not outside of the square root. So here's your original y, right? The y, this is the value of your y coordinate. When x is 1, square root of 1 is 1. X is 4, square root of 2. So those are your y's. You're not going to change the sign of those. Actually, what you're going to do is change the sign of the x. And so what, in other words, this is inside. The operation being square root, right? I shouldn't just put that like that without an input. I'll just say in Word, square root. Okay. And so what happens is, for the same value of x, like when you put a 4 in here, you actually don't get a real number for an output. So what this does is it changes the domain. Notice you need this expression, negative x, to be greater than or equal to 0. Well, with the negative, divide both sides by -1, the domain becomes x is less than or equal to 0. And so this actually is going to take all our original inputs. Those no longer work. You have to go and plug in the negatives. And when you plug in -1, now you get the square root of 1, which is 1. When you plug in -4, the opposite of that is 4, and its square root is 2, and etc. Plug in -9, its opposite is 9, and you get out, square root of 9 is 3, so that's about here. And so we end up, sorry, not the best graph here, but with a reflection through the y-axis. Now with this particular one, a lot of these functions are even. So like this one, if we had plugged negative x in here, we would just get the same picture because it reduces to the same thing as, you know, absolute value of negative x is equal to absolute value of x, is what I'm trying to say. So you just get the mirror image. That's why I use the square root function, because that's one of the ones we have that we don't have a mirror image. In that, you know, when I say one of the ones we have, I mean in that library of functions we looked at last time. Okay, so in the next page, that sums that up. So this f at x is your y, right? And this just means you're changing the output of the original of this. Okay, so this is, I should put this is your y. Then this is the opposite. Okay, so this reflects it through the x-axis, and then this one is opposite of x. Whoops, this is what happens when you cut and paste. This should just be f at x here. Sorry about that. So x was the input. Now you're going to change the sign of the input, so you get a reflection through the y-axis. I gotta remember to fix that typo. Okay, so that's our first set. Those are our reflections. Definition of reflections. Our next set, I'm going to use a different function, but we could still use square root function here. It doesn't matter which one we use to show how this works. It's all always going to work. We start with our basic shape y equals x squared. Go back to my pencil here. So 0, 0, 1, 1, 4, 4. Okay, so that's our, you know, our squaring function, which gives us our parabola. You memorize your parabola. Remember out 1, out 2, up 4, out 3, up 9. Remember that basic shape. It'll help you. Okay, so now we have y equals x squared. So again, if you think of this as your original output f at x, that's your y, right? Do y equals f at x. Now what's going to happen if you add 4 to each of those original y's? So in here we had y as x squared. Now we're going to add 4. 1, 2, 3, 4. Here our y was 0. We're going to add 4. The new output is going to be shifted up 4. And so all of these original y's, 2, 3, 4, are just going to be shifted up 4 units. That's going to come here. That one's going to come here. It doesn't change the shape at all. It's still the same shape. It's just shifted up. Vertically. Up 4 units. So if you understand that, the next example is not too difficult. The -5, I have another graph here, but we can actually just put it right here. You're just going to take this original parabola. Now you're taking 5 away from each y. That's just going to pull the whole thing down 5 units. So we end up with, so remember, here's your vertex, comes down here, out 1, up 1, out 2, up 4. And here is, so that, whoops, drew my line in the wrong spot. That one is up 4. This one, y equals x squared minus 5, shifts, oh, sorry, getting ahead of myself. I was going to say y equals x squared down 5 units. That's an S there. Okay, so these are our vertical shifts. And the way a definition written here, I just say plus k, but k can be positive or negative in this case. So it's going to go up k units if k is positive. So that was like the example y equals x squared plus 4. And it's going to go down k units if k is negative. And so that would be like y equals the x squared minus 5 that we looked at. So the original f at x here would have been the x squared in that example. All right, the next set then, we have, so we're going to use x squared again. It's a nice one to use. So I'll start with that. Okay, and now look at these and notice the plus 4 and the minus 2 are inside the operation again. Anytime the operation is happening under the function, like the original function is the x squared, the squaring, because that addition or subtraction of the number is, inside there, it's going to affect it horizontally rather than vertically. So this is affecting x. So if you think about your original input, when you, here for this one, when you get 0 squared and get 0, what number is going to make this plus 4 balance out so you get 0 squared? And of course it's negative 4. Negative 4 plus 4 is 0, and then 0 squared is 0. And so actually a lot of students think it's going to shift over to 4, but it ends up shifting back to negative 4. Now notice, okay, so when x is negative 4, we're doing just y equals x plus 4 squared here. We get y equals 0 squared. Now here's where I want you to think about that, go out 1, up 1. Notice when you go 1 away from negative 4, in either direction, so one direction you'd get negative 3, and the other direction you would get negative 5. Okay, so the y, negative 3 plus 4 squared, and then the negative 5, you'd get negative 5 plus 4 squared. Notice that's when you're going to get the 1 squared or the negative 1 squared like you did in the original. And so here's where you're going to get the 1. And then you can do a similar thing for negative 2 and negative 6. Those are the things that are 2 units away from, the center, which is the negative 4. So notice negative 6 plus 4 is negative 2. Negative 2 plus 4 is 2. And the 2 squareds are what give you the 4. And so the shape ends up being the same. It actually shifts to the left 4 units. So even though it says plus in here, that makes people want to think right, of course. It actually goes the opposite. So when we graph y as x minus 2 squared, now you can probably figure out what's going to happen, right? So again, our original, this time I'll use the second graph. It gets a little messy on here otherwise, because they overlap. So here's my y equals x squared. So this time, this vertex, to balance out the y is x minus 2 squared, we need to make that a 2. And then 2 minus 2 squared will be 0. That's where the vertex is going to go. And then notice when you go out, 1 in each direction, 1 minus 2 gives us the negative 1. 3 minus 2 gives us the positive 1. So that's where you'll get the 1 and 1. And then, of course, 0 here would give us the 4. 4 minus 2 is 2. 2 squared is 4. And so that's where the new center comes from at the number that makes this 0 in here. And so, of course, this is a shift to the right of 2 units. So the blue one is x minus 2 squared. All right, so the vertical shift, the plus, whoops, that's the reflection. Sorry, no, it's not. Oh, I should have left a little space here. The definition says reflection, but these examples are my shifts up and down. So the vertical shifts up and down, remember those have the addition and subtraction of the number outside of the f at x. Here, whatever the operation is, in that example, x squared. Here, the addition and subtraction of the number is under the operation f at x. So notice in the definition here, that's why it's written like this. The number is added under the operation. Now, just like before, this number in here can be positive or negative. So if it's a positive, so like in the, let's see, what examples did we do again? Oh, x plus 4 squared. That'd be the example here that we did. So that's positive number in there. Then it's going to move it to the left. And then in the case where this is a negative, so you're subtracting a number, then you're going to move to the right. So it does the opposite of what your instincts might initially tell you. Okay? All right, so now we're going to do a couple examples where we put these 3 sets of transformations together. We're going to learn 2 more sets though. All right, so the first one here, when you look at this, you want to say, okay, well, what is my basic operation I'm dealing with? And that's the cubing. And so you start with the cube function. Again, memorize what those look like. 2, 8, 2, 8. So here's our y equals x cubed. And then I always start from the inside of the operation and kind of work your way out. There's nothing happening inside this operation. So the next thing we would do is look at this negative and ask ourselves, what's that going to do? And that's going to reflect it through the x-axis. And then the last thing is going to be this vertical shift, and that's going to shift it down 5. Here, let me write this over here. There's not enough room. So this is a reflection through the x-axis, and this is down 5. But the basic shape is still the same. Okay, so this, you can do it in 2 steps or you can do it in 1. You can put the, if you want, I'll put this in pencil because this isn't good. I'll put the final answer in blue. All right, so this reflects up here. Anything on 0, 0 stays the same. This comes up here. This comes down here. So this graph, and each step that you take, you know the equation of the graph. So these almost, these aren't meant to be the same. Let's see. I don't know if I have another color handy. usually always have something red around for grading, but I'm not finding anything. Oh, here, I have a highlighter. I'll just highlight this one to kind of separate it. So this one, it's not the final answer, but just wanted to make it look different. So that one is y equals negative x cubed. And then the final answer, we're going to shift that down 5. So down 5, down 5, down 5, 2, 3, 4, 5. This one's, of course, going to be off the graph, so I'm not going to put that point on. But we can still basically get the shape. So the blue graph is our final answer. That's our y is negative x cubed minus 5. Okay, the next one, this is the cube root function. So we want to start with y equals x cubed, which looks like a lot like the y equals, did I say y? We start with a y equals the cube root of x, which looks a lot like y equals x cubed. Sorry if I said that wrong. Okay, so here we have our original. Whoops, and I almost wrote x cubed. It's cube root of x. Okay, so the plus, start from inside. This one does have something inside. The plus 3 under the function, excuse me, is going to move it left 3, not right 3, left 3. So remember, what is that balance point that would create a 0 under here? Because you want to know where this 0, original 0, is going to go. And that's going to go back here. And so everything just moves back 3. You have basic shape, of course. Okay, so again, I'll use the green to show that one's a new graph. That's y is, the green one is y equals cube root of x plus 3. All right, and now the final answer is going to have this moved up 2. So take the green graph and shift everything up 2. So you want to memorize where the relationship of those, at least, center 5 points, I would say, are. Like in the quadratic I used, well, this wasn't the quadratic, sorry, but in the, where did it go? There it is. Quadratic, I used these 5 points. In the cubic, I used, these 5 points. In this cube root, I'm using these 5 points. And then if it gets off the graph, you can drop one of them, but you should at least have, as many as you can of those 5 on the graph. Okay, so 2 over 1, 2, 3, 4, 5, 6, 7, 8. Or I could have just used this up 2. And then that one's going to be off the graph, so I'm not going to use it. This turn probably isn't strong enough. Okay, so there we have y equals cube root of x plus 3 plus 2. Final answer. Okay, and here I have one that's not using one of the elementary functions that we learned in the last section. It's just a line segment. And I said, well, this is y equals f of x. So if I know the shape of this, see, the point of this example is it doesn't matter if it's one of those elementary functions or not. You can always use this. We know the shape. We know this is y equals f of x. And if we know our transformations, we can graph this then. This inside here is going to reflect it through the y-axis. And then the negative 3, that'll move it down 3. Okay, so this, I'm going to do this all in one this time. This is going to get reflected over here and then shift down 3. This y-intercept, it's not exactly at 4. It's a little before 4. That's going to stay on the y-axis when you reflect it. But then when you move it down 3, 1, 2, 3, you have to remember to, put it a little bit below 1 then. This over here, 3 units away from the y-axis, gets reflected over here. Whoops, but then I got to move it down 3. So 1, 2, 3. So notice how they're lining up. If you're keeping track of what you're doing correctly, you should get the same shape, oriented differently, but it's still the same shape. And so we have, actually I'll use the blue here, this graph. So just use your, those key points to help you. And this is y is f at negative x minus 3. Okay, let's look at the next set of transformations. We want to sketch the graphs of, so we're back to the absolute value function compared to absolute value of x. This time we have a 2 out front, multiplied times absolute x, and then a 1/2. So what are those going to do? All right, so let's start with our original. There's our original. Okay, so now because the 2 and the 1/2, let's focus on the 2. Because the 2 is outside of the absolute x, this is going to affect the y coordinate. Here's your, you have your original y's that are, up 1, up 2, up 3, up 4, etc. Now you're going to take that result times 2. The only thing that changes if you were going to find this function value is now you're going to double the old answer. And so what happens when you double the y, well, 0 times 2 is still 0, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. And so what's going to happen is you get this exaggerated v because, of course, when you double something, it depends on its value. So the original value, whoops, 3 should have went to 6. I have that one in the wrong spot. So the larger the y is, the more effect that doubling has, is what I'm trying to say. So if you look vertically here, here's your original 3. Now you've got 6. So if you understand that as a space, you can kind of estimate where the doubling would go. Now we don't need to estimate if we actually know the values, but in an example like, say we had this graph, say that was y equals f at x, and I ask, we don't really know the x's and the y's here, I'm not going to put them in, but if I asked you to graph 2f at x or 3f at x, let's say it's 3f at x, you would kind of estimate here, that, and then triple that, that peak would come up here. All the zeros would stay the same. So all of these y's, original y's, are going to get tripled. So the farther you get away from the x-axis, the more stretched this is going to be. The correct word is stretch. So this, triple maybe be about here, and then this tripled, it's going to go way up here. So this is going to get stretched or pulled up. This gets stretched. And then these are negative y's down here. Well, if you take them times a positive 3, they're still going to become 3 times as far away from the x-axis. So this is still tripled. It's still going to be negative. Maybe about right here. So you get this exaggeration of the graph. So as long as you know what the, if you have the original, you can imagine the higher this number is, the more stretched out that's going to be. But the zeros, the x-intercepts in other words, they don't move because 0 times anything is still 0. Right, I should label this blue graph. This was 2 absolute value of x. So what happens with these is you're going to multiply each of the y coordinates times that coefficient. Now we use 2. In this example I use 3. But it can be any number there, of course. It could be 5.5 and you would use a multiple of 5.5. Now this one has a half. Now notice the half is smaller than 1. And so what's going to happen with this one is instead of a stretch, it's actually going to shrink. So let's go back to this absolute value of x function. So now I'm going to take each of these y's and multiply them times a half. Again, the 0 times anything is still 0, so that stays the same. But when you have 1 times a half, notice the point is now going to come below the graph. 2 times a half is 1. 3 times a half is 1 1/2, or 3 halves. 4 times a half is 2. And so this side here, notice they're all half as high as the original. And of course we're going to get the same thing on the other side. So this blue graph, y is 1/2 absolute value of x. So vertically, you take the original, and whatever this height was, this height is half as high. Okay, now we only considered these coefficients to be positive. If they are negative, that's going to be the separate reflection. Okay, so you would take, if this is -2 absolute x, you would first find 2 absolute x, and then you would reflect it. So it would have the same shape as 2 absolute x. So in these problems, I should maybe include here that a is greater than 0 in this definition. So we've got our vertical stretches. So I'm calling this one a stretch, and this one is a compression. It's getting sandwiched towards the x-axis. There's nothing on the other side of the x-axis, but if there were, the whole thing would just get sandwiched in between, or towards the x-axis. Okay, so this, if a is greater than 0, you're going to get a stretch, and if a is here, actually, sorry, that should say a is greater than 1. That's why I like to use a pencil. I shouldn't use a pen. A is greater than 1, and then if a is between 0 and 1, you get a compression. And then if a is negative, then you have a reflection. That's a separate transformation. Okay, so all of these a is positive. What you should do then is multiply for either of these. It doesn't matter if a is greater than 1 or less than 1. You multiply each original y coordinate by a to obtain the new y coordinate. I'll just abbreviate that. Okay? All right, I'm going to take a little pause here, and then we'll talk about our last set, which will be our horizontal stretches and compressions.